To this video on the electric potential, and I'm calling it part two, although it's probably more like part three or four based on the videos that we've had so far. And if you haven't watched those, please go back again and take a look at those. Now, right here at the top, I have this chart that's very specifically laid out to help you maybe combine or compare and contrast these different quantities, because we've had four major ideas: the electric field, the electrostatic force, the electric potential, and the electric potential energy. Now, they are arranged horizontally this way by these two being vector quantities, meaning that if I'm trying to find, let's say, the net electric field at a point in a multi-source um, situation, I would need to consider the direction of the field at that particular location. Down here at the bottom, the electric potential and the electric potential energy, just like energy always is a scalar quantity. Meaning if I have, two or more charges and I'm trying to figure out the potential at a particular location, I don't consider the direction because there isn't direction or orientation associated with the potential and therefore the potential energy. But vertically, these are arranged regardless of their vector or scalar properties. So vertically, these two are arranged based on a source and a location. Now, what I mean by that is you could have more than one source, but at least one source. So say, here's my source, and here's a location. So the field or the potential are defined as a point within a field, a location within a field. Whereas the two on the right here, if I vertically combine the two up here, these two deal with a source and no longer just a location, but another object, and it could be, a positive or negative charge, whatever. So we could call it a source and a test, or a source and a point charge. But these deal with the two interacting things, two interacting charges, and here we're dealing with a source and a location. So familiarize yourself with that so that looking forward, you have those things down and you have them classified well in your mind. Now, what we're going to look at is kind of where we left off before, and we're trying to look at equipotential lines relative to field lines. And one of the main things that we talked about was that they're going to be always at right angles to one another. Now, if I were to describe this dashed line or any of the dashed lines, I'm going to use 2 points on this line. So I'll pick here point A and then point B. Now, if I were to move something from point A to point B, right, or if I were to compare point A to point B, I could compare a few different things. I could say that the electric field at A is equal to the electric field at B because they have the same radial distance from the source. Now, let's compare the electric potential at A to the electric potential at B. Well, we could say that the delta V, which is V, let's just say VB minus VA, that's actually 0. And if the difference is 0, that must mean it's on a line of equipotential. So on a line of equipotential, if you were to place a little positive test charge right here, you could even place a little negative test charge, and I were to try to move it against or along this line, what I would say is that the field does no work. And I could show that using this idea. I already established this, and I'm going to write it out in full script here for a second. I'm going to say F dot delta X. I know that F is Q times E, and that's delta X. And then E delta X, remember, is delta V, and that's the delta V here. Well, we can see if there's no difference in potential, then there is no work done by the field to move it from A to B. And so that's a very important concept to get used to so that you can understand why there's no work done, and that's because there's no potential difference. So in terms of charges, it's important because it's not always exactly the same when you think of it in across different equipotential lines. So if I'm going from, let's say, A, and let's call this point over here C, that is going to require some work, right? So I'm going to say here, I'll use the same thing. Q is, remember, the little source charge, that right there, I mean the little test charge, that little point. So Q times, and this would be VC minus VA, and that is not equal to 0, and so there would be work required for it to move that way. Now we would say that this would require external work specifically because a positive charge is not going to move towards a positive charge. The field will push it outwards, as is indicated here by the field lines. So that's pretty important. Now, something else to compare. We always have to say that there is some relative potential, right? And so if I were to graph the potential versus the position, I know that as r approaches infinity, v will approach 0. And so I know right at the source charge, right here at this position 0, I have my full potential right close to it. But way, way, way out here at infinity, there is 0 potential. So if I said to you, how much work would it take to move a charge from infinity to point C? Well, to calculate that, I would use my work expression, Q delta V, and I would say V at point C minus V at infinity. Well, I know V at infinity is 0, so I'm really just needing to calculate the potential at point C. And the potential at point C can be calculated using this expression over here. And so that's not too bad at all. Now, a lot of people, it throws them off because they think, well, to move something all the way from infinity here must take an infinite amount of work, but it doesn't because there is no potential at infinity, and as I move closer, it changes. So that's an important concept to be able to kind of conceptualize in your mind. Now, for the eagle-eyed among you may have noticed that as we move further out away from the source charge, the equipotential lines space out more and more and more, and that symbolizes that the potential is decreasing as we move outwards. Also, the field lines, right, are indicating that this is a non-uniform field because it's changing as we go out. Now that's in contrast to this image here on the left where I have field lines pointing left to right. And go ahead and pause if you need more than about 4 seconds to answer where is the region in this field that's more positive and the region that's more negative. Well, hopefully you realize that this is more positive because field lines conventionally always point away from the positive side and they point toward the negative side. And the way that I could set up a field like this would be to take a plate with a positive charge and a plate with a negative charge, and I could set up this. And this is a uniform field. And take about 4 seconds or so to decide, why is this a uniform? Well, it's uniform because the field lines, or we know it's uniform because the field lines indicate that they neither converge nor diverge, and so that must mean that the field is uniform. And so then the potential, the equipotential lines, take a few seconds to go ahead and try to sketch those in. Good, well hopefully you realize that those equipotential lines, and I'll just draw 2 of them in here, should be vertical and because they're always perpendicular. So moving anything sort of in this scenario up and down along this equipotential line would require no work, where the field does no work to do that. But moving something from this point to this point may or may not require work, or the field may or may not do work depending on what the charge is itself. So we would describe this as the place of high potential, and that is based on the convention, and this is the place of low potential. So one thing to note here is that if I move let's put a positive charge right here, and we'll call this location A and this location B. If I'm moving from point A to point B and it's a positive charge moving that way, the field is doing work and it will require no external work because that will naturally occur. We could also say that this object right here would increase its kinetic energy as it moved this way. All of the old energy and work theorems apply here. Another thing that we could say is if I was trying to move the same positive charge from B to point A, that would require external work. So let's also look at this. If I move this positive charge from A, or if it moves from A to point B, that's going to be a negative electric potential change. So it's decreasing the electric potential energy between this and the little particle over here, okay? Or this and the little particle over there. But if I move from B to A, that takes external work, and I'd have an increase in electric potential energy moving it relative this way. Okay, so at this point we have a fairly good understanding of all of the pieces of information with all the practice that we've done, and now we're going to start to move into this idea of how do we actually get a field set up? Like, how can we physically make an electric field? In addition to that, we want to learn how to actually make a field map. And so the next thing to do will be to figure out what will I need to do in order to measure the field. And so those two things together will be what we discuss in the next videos or so, and we'll take a look. So what I want you to do is a challenge for the end of this video. So the challenge time is to think about how could I set something up like this, getting this plate positively charged and this plate equally but oppositely charged so that I could create a uniform electric field. Go ahead and think about that a little bit, and in the next video we will figure that out together.